Let's dig a little deeper into the lead iodide experiment. The purpose of this experiment was to explore the concept of a limiting reactant in the laboratory setting. However, we're also going to analyze the data and verify the formula of the yellow solid we made, lead 2 iodide. Now we can easily do this with our ion table, knowing that lead 2 is a Pb2+ ion and iodide is an I- ion. To get a neutral ionic substance, we would need 1 lead 2+ ion and 2 I- ions, which would give us a formula of Pbi2. But back in the day, before scientists knew about atoms, and definitely before scientists knew about ions, they were able to determine formulas of compounds. They did it in a very similar way than we did it in the lab. So if you remember, we had our test tubes full of our yellow Pbi2 solid. We also had a mass of the test tube when it was empty. So if we take those two masses and subtract them, we can get the grams of lead iodide that were produced. So we're going to use some sample data to make sure that we see the right thing in order to verify the formula of lead 2 iodide. So in the lab, the next thing we did with our data was graph it. So we had a graph of our test tubes on the x-axis and the grams of lead iodide inside of each test tube on the y-axis. And when we graph our sample data, it should look a little something like this. When we did our lab, it should also have looked something like this, where the mass of lead iodide seems to plateau and peak at about the third test tube. So the amount of lead iodide produced will level off around the third test tube. So we can use this information to determine the formula of lead iodide. For that, we will first need to know how many moles of lead and moles of iodide we added to each test tube. I'm going to go through a sample calculation for each one of these problems. I'm going to use test tube number 1 as my example. So to find the moles of lead, I'm going to take the volume of lead nitrate that I added to test tube 1, convert it to liters. And then to find the moles, I'm going to multiply by the molarity. The molarity was 0.500 moles in 1 liter of lead nitrate. So you can see that gets my liters of lead nitrate to cancel off. And if I multiply those two numbers together, I will find the moles of lead nitrate that I added to test tube number 1, which is 0.00025 moles. I'm going to go through a similar calculation to determine the moles of sodium iodide I added to test tube number 1, and in fact, all of the test tubes, because we always added 5 milliliters of sodium iodide to every test tube. So I'm going to convert that 5 milliliters to liters, and I'm going to multiply by the concentration, the moles per liter. There's 0.400 moles of sodium iodide in every liter of the solution. If I multiply those two numbers together, I will find that every test tube got 0.0020 moles of sodium iodide added to it. If I did a similar calculation for test tube 2, 3, 4, and 5 in terms of the lead nitrate, I would see that I added 0.00050 moles of lead nitrate to test tube 2, 0.0010 moles to test tube 3, 0.0015 moles to test tube 4, and 0.0020 moles to test tube 5. Now I can use this information to determine the formula of lead 2 iodide experimentally. So what we're going to do is find the test tube where the amount of lead iodide started to level off. And as we discussed, that's test tube number 3. I'm going to use the data from the data table to get the moles of iodide and the moles of lead I added to test tube number 3. You can see I added 0.0020 moles of iodide and 0.001 moles of lead. I could set up a little ratio here. If I take 0.002 and divide by 0.001, I will see there is a 2-to-1 ratio. I need 2 moles of iodide for every 1 mole of lead. If I put that in a formula, it would look like this. Well, we don't write ones as subscripts in a formula. It would be PbI2. And as I already explained, we can get the same thing from using our ion table. If I have Pb2 plus ions and I minus ions, I would need 1 Pb2 plus and 2 I minuses to make a neutral ionic compound with a formula of PbI2. The formula we determined experimentally matches what we should have gotten using the ion table. That means we had good laboratory technique. So let's take this a step further. The next question asks, which test tubes had excess lead ions and which test tubes had excess iodide ions? Let's go back to that data table and look at this a little bit more carefully. Test tube number 3 had the perfect amount of iodide ions and lead ions. Both ions completely reacted. So test tube 3 doesn't have an excess of iodide, it doesn't have an excess of lead. But the other test tubes have an excess of one of the ions. You need 0.001 moles of lead to react with 0.002 moles of iodide. Notice we have 0.002 moles of iodide in every test tube. But in the first 2 test tubes, we do not have 0.001 moles of lead. That means all of this lead is going to react, and we're going to have some leftover iodide ions. The reverse is true for the last 2 test tubes. We have more than enough lead ions to react with all of this iodide. Therefore, test tube 4 and 5 is going to have an excess amount of lead ions. Make sure you have circled the correct answer choices for 1 through 5. Now for the most important part of this post-lab activity. I'm going to show you for the first time this year how to write the total balanced equation, total ionic equation, and net ionic equation for the reaction that happened in this lab. This will be the first time of many throughout the rest of the school year that you will be completing this type of procedure. So I'm going to start with the total balanced equation. That involves both of my reactants, lead nitrate and sodium iodide. They reacted to form products. This is an ionic precipitation reaction. One of the products was a solid, the other was an AQ. We have to figure out what those products are. To do that, we need to split our reactants into their ions. This is why we take those ion quizzes. So PbNO3 splits up into Pb2 plus and NO3 minus. Sodium iodide splits up into Na plus and I minus. During an ionic precipitation reaction, the cation from one substance is going to pair up with the anion from the other substance, and vice versa. So one of the products I'm going to get involves lead and iodide ions. So let's figure out for the third time during this activity what the formula for this product would be. If I have Pb2 plus ions and I minus ions, I would need 2 I minus ions and 1 Pb2 plus ion to make a neutral compound. Therefore, the formula would be PbI2. I do not yet know if it's a solid or an AQ. So I have my parentheses set up, but I'm going to leave those empty for right now. My other product involves sodium and nitrate ions. So I have Na plus and I have NO3 minus. How many of each ion do I need to make a neutral substance? I would need 1 cation and 1 anion. Therefore, the formula will be NaNO3. So that is my total equation. It is not yet balanced, but that is my total equation. Before I balance it, I'm going to figure out, is PbI2 the solid or is it AQ? Is NaNO3 a solid or is it an AQ? For that, we're going to use the back of our ion table. In the rows, I have all the cations that we might use in this class. And in the columns, I have all the anions we might use in this class. So for lead 2 iodide, I'm going to find lead 2 plus in the row. I'm going to find I minus in the column, and I'm going to go to where they intersect. There I see an I. Well, what does I mean? I means insoluble, will not dissolve in water. So this is the substance that forms a precipitate. It needs a solid after its formula in the equation. We already knew that. The yellow solid we made was lead iodide. The other substance was sodium nitrate. So I'm going to find sodium Na+ on my ion table, and I'm going to find nitrate on my ion table. I'm going to see where they intersect. And I see there it says S. S does not mean solid. S means soluble, which means it will dissolve in water, which means this substance will have an AQ after its formula in the total balanced equation. As a side note here, I will point out that Na+, if you look all the way across the row, any substance with Na+ in it is always soluble. Same for nitrate ions. If you look down the column, any substance that has nitrate ions in it will always be soluble. So I could fill in PbI2 as the solid and NaNO3 as the AQ. So I do not make any mistakes later on in the TIE and the NIE. I'm going to write down PbI2 solid in both of those reactions as the product. Okay, I'll explain why here in a second. Before I move on to the total ionic equation, I must balance this equation that I've written here. To do that, for this reaction, I will take you through it pretty quickly. I need 1 lead on both sides. Okay, I have 2 nitrates on the reactant side. I need 2 on the product side, so I need a 2 in front of NaNO3. And that now means I have 2 sodiums on the product side. I need 2 sodiums on the reactant side. And you can see I also have 2 iodides then on the product and reactant side. I have written the total balanced equation, the TBE. Now I'm going to write the total ionic equation. To do that, I take all the substances that are AQs and I split them into their ions. If it's a solid, liquid, or a gas, I do not split it into its ions. That's why, so I don't make a mistake, I wrote down PbI2 solid in my next 2 reactions right away. Everything else is AQ after it, so I have to break it up into its ions. And if you follow the procedure I do up here, you will already have this done. So then you just need to use the subscripts in the formulas and the coefficients in the reaction to find out how many you have. So I'm going to write the total ionic equation starting with lead nitrate. Okay, I have Pb2+ ions. How many do I have? Well, the formula has 1 Pb2+ in it, and the coefficient is a 1, so that means I just have 1 Pb2+. Okay, how many NO3 minuses do I have? Because that's the next ion in my total ionic equation. Well, I had 2 in the formula, and my coefficient is a 1, so that means I have 2 NO3 minuses. Okay, now I know sodium iodide breaks up into Na+ and I-. Those are the next ions on my reactant side. So I have Na+. Now in the formula, the subscript after Na, there isn't one, which means there's just 1 of them. But when I balance the reaction, I need 2 of those. So if I use my subscript and coefficient, I figure out I need 2 Na+. Same is true for I-. I would have 2 of those. I have now written the ions on the reactant side. On the product side, PbI2 is a solid, so I'm not going to break it into ions. NaNO3 is an AQ, so I will break it up into ions. We already know Na is Na+. I have 2. Okay, the coefficient times the subscript gives me how many of those ions I have. Same goes for nitrate. I only have 1 nitrate in the formula, but I put a 2 as a coefficient. That means I have 2 NO3 minuses. I have now written the total ionic equation. Now I just want the ions that participate in the reaction. So to do that, I will write the net ionic equation. To find the ions that participate in the reaction, I first have to find the ions that do not participate in the reaction. They just watch the reaction happen. Therefore, they're known as spectator ions. I'm looking for the ions that appear on both sides of the equation, both as a reactant and a product. You can see I have NO3 on both sides of the reaction. I also have 2 Na+ on both sides of the reaction. Those are the spectator ions. So I can circle those, I can cross those out, whatever I need to do. However, what I don't cross out those are the ions that I write for the net ionic equation. So I didn't cross out Pb2+, so I have one Pb2+, and I have two I minuses. And that will get me one PbI2. I've just written the net ionic equation. To wrap up this post-lab activity, we're going to label our 5 test tubes. To do this properly, we're going to look at the net ionic equation at the bottom of page 2, and we can also look at the excess ions that we circled on page 2. Okay, so the first thing we're supposed to do is label the precipitate in the solid in each tube. Well, from our net ionic equation, we know the solid is PbI2. So in each one of these test tubes, at the bottom, I have solid PbI2. Now I have to show which test tubes have the ions in solution. Which ones have sodium, nitrate, lead, and iodide ions in them. Well, remember, sodium and nitrate were spectator ions. They did not participate in the reaction. That means you can find sodium ions and nitrate ions in all 5 test tubes. They did not react. They will always be in ions in the solution above the precipitate. Okay, now the third tube is done because in the third tube we had the excellent ratio where all the lead and all the iodide ions reacted to make the most PbI2 as you could. But in test tubes 1 and 2, we had excess of one of the ions. If you look back on page 2, you would see in those 2 test tubes we had excess iodide ions. In test tubes 4 and 5, all of the iodide reacted, but we had excess lead. So test tubes 4 and 5 have excess lead ions. That concludes the post-lab analysis of the lead nitrate lab.